Earth's origin and evolution. The origin and evolution of Earth is a complex and fascinating subject that scientists have been studying for many years. The current scientific understanding of Earth's origin and evolution is based on a variety of evidence, including geological, chemical, and astronomical data. Here is a brief overview of the prevailing theories. Formation of the solar system. About 4.6 billion years ago, the solar system began to form from a giant molecular cloud composed mostly of hydrogen and helium. A nearby supernova explosion or a passing star's gravitational disturbance likely triggered the collapse of this cloud, leading to the formation of a rotating disk called the protoplanetary disk. Accretion and differentiation. Within the protoplanetary disk, tiny dust particles collided and stuck together, gradually forming larger bodies called planetesimals. These planetesimals further collided and accumulated to form protoplanets. The protoplanets continued to grow through a process called accretion. Eventually, a protoplanet the size of Mars, called Theia, collided with the early Earth, resulting in the ejection of debris that eventually formed the Moon. Early Earth. During its early stages, Earth was a hot and molten planet, undergoing intense bombardment from asteroids and comets. The heat generated by the impacts, as well as the decay of radioactive isotopes within Earth, caused the planet to partially melt and differentiate into layers. The heaviest materials sank to the center, forming the core, while lighter materials formed the mantle and crust. Formation of the atmosphere and oceans. As Earth cooled down, water vapor in the atmosphere condensed and fell as rain, leading to the formation of the oceans. The early atmosphere primarily consisted of volcanic gases, such as water vapor, carbon dioxide, nitrogen, and traces of methane and ammonia. Development of life. The earliest evidence of life on Earth dates back to around 3.5 billion years ago, in the form of fossilized microbial mats called stromatolites. These early life forms were simple, single-celled organisms that thrived in the Earth's oceans. Over time, life evolved and diversified, leading to more complex organisms. Plate tectonics and continents. Earth's outer layer, known as the lithosphere, is divided into several large and small tectonic plates that float on the semi-fluid asthenosphere below. The movement and interaction of these plates give rise to various geological features, including mountains, oceanic trenches, and volcanic activity. Plate tectonics also played a crucial role in the formation and breakup of continents over billions of years. Climate evolution. Earth's climate has undergone significant changes throughout its history due to a variety of factors, including volcanic activity, variations in solar radiation, changes in atmospheric composition, and the evolution of life itself. These changes have led to periods of global warming, cooling, ice ages, and mass extinctions. It's important to note that our understanding of Earth's origin and evolution is continually evolving as new scientific discoveries and evidence emerge. Scientists use a combination of observational data, laboratory experiments, computer models, and theoretical frameworks to refine our understanding of this complex process. Formation Earth. The formation of the Earth is a fascinating scientific topic. According to current scientific understanding, the Earth was formed approximately 4.6 billion years ago through a process known as accretion. The formation of the Earth began with the collapse of a giant molecular cloud, composed mostly of hydrogen and helium, in a region of space. This collapse led to the formation of a rotating disk of gas and dust known as the protoplanetary disk. The gravitational forces within the disk caused the material to clump together, forming small planetesimals, which were the building blocks of planets. Over time, these planetesimals collided and merged, growing in size through a process called accretion. The larger these planetesimals became, the stronger their gravitational pull, allowing them to attract even more material. Eventually, through numerous collisions and mergers, these planetesimals formed a protoplanet, which eventually became the Earth. During its early stages, the Earth experienced intense heating due to the energy released from collisions and the decay of radioactive elements. The heat caused the Earth to partially melt, forming a molten interior. As the protoplanet continued to accrete material, its gravitational force increased, attracting more and more matter. As the Earth grew in size, it began to differentiate. Heavier elements sank toward the center, forming the core, while lighter materials rose to the surface, forming the crust. This process of differentiation gave the Earth its layered structure, with a solid inner core, a liquid outer core, a mantle, and a crust. The early Earth was also bombarded by asteroids and comets, which contributed additional material and water to the planet. The impact of these celestial bodies had a significant influence on the Earth's geological history and the development of its oceans and atmosphere. Over millions of years, the Earth's surface cooled, allowing for the formation of a solid crust. The release of gases from volcanic activity and other processes led to the formation of the Earth's atmosphere. Water vapor in the atmosphere condensed and fell as rain, resulting in the formation of oceans. The formation of the Earth is a complex process that scientists continue to study and refine their understanding of. By examining rocks, minerals, and other geological evidence, as well as through computer simulations and observations of other planets and celestial bodies, scientists have pieced together the story of how our planet came to be. Size and shape of Earth. The Earth is approximately a sphere, but its shape is not a perfect sphere. It is an oblate spheroid, meaning it is slightly flattened at the poles and bulges at the equator. This shape is due to the Earth's rotation, which causes the equatorial regions to experience centrifugal force, pushing the material outward and resulting in the bulge. The average radius of the Earth is about 6,371 kilometers, 3,959 miles. The equatorial diameter, measuring from one side of the Earth to the other through its center, is approximately 12,742 kilometers, 7,918 miles. The polar diameter, which measures from the North Pole to the South Pole, is slightly shorter at around 12,714 kilometers, 7,900 miles. The difference between the equatorial and polar diameters is about 42 kilometers, 26 miles. In terms of circumference, the Earth's equator measures approximately 40,075 kilometers, 24,901 miles. The Earth's surface area is approximately 510 million square kilometers, 196.9 million square miles. It's important to note that the Earth's shape is not a perfect spheroid, as the distribution of land masses, variations in density, and gravitational forces from other celestial bodies contribute to local irregularities in the shape. These irregularities are relatively small and do not significantly affect the overall shape and size of the Earth on a global scale. Orbit and rotation Earth. The Earth orbits around the Sun in a slightly elliptical path, which means its distance from the Sun varies throughout the year. This path is called an orbit. The Earth's orbit is not a perfect circle but is rather an ellipse, with the Sun located at one of the foci of the ellipse. The time it takes for the Earth to complete one orbit around the Sun is approximately 365.25 days, which we refer to as a year. This extra fraction of a day is why we have leap years every 4 years to keep our calendar in sync with the Earth's orbit. In addition to its orbital motion, the Earth also rotates on its axis. The Earth's axis is an imaginary line passing through its north and south poles. It takes the Earth about 24 hours to complete one rotation, which gives us our day and night cycle. The combination of the Earth's orbit around the Sun and its rotation on its axis results in the cycle of seasons and the variations in day length throughout the year. The tilt of the Earth's axis, approximately 23.5 degrees, is the main factor responsible for the changing seasons. As the Earth orbits the Sun, different parts of the planet receive varying amounts of sunlight, leading to the different seasons experienced in the northern and southern hemispheres. When one hemisphere is tilted towards the Sun, it experiences summer, while the other hemisphere, tilted away from the Sun, experiences winter. The equinoxes occur when the tilt of the Earth's axis is perpendicular to the Sun, resulting in roughly equal day and night lengths worldwide. Magnetic field Earth. The Earth has a magnetic field that extends from its interior into space. This magnetic field is generated by a process called the dynamo effect, which is driven by the movement of molten iron and nickel in the Earth's outer core. The Earth's magnetic field is often compared to that of a bar magnet, with a magnetic north pole and a magnetic south pole. However, the Earth's magnetic poles are not aligned with the geographic poles, the north and south poles, but are instead slightly offset. The magnetic field of the Earth has several important functions and effects. Navigation. The Earth's magnetic field plays a crucial role in navigation. Compasses align with the magnetic field, allowing us to determine direction and navigate accurately. Protection from solar radiation. The magnetic field acts as a shield, protecting the Earth's surface from the harmful effects of solar radiation. The field deflects charged particles from the sun, known as solar wind, preventing them from directly reaching the Earth's surface. Auroras. The interaction between the Earth's magnetic field and charged particles from the sun leads to the formation of auroras, northern and southern lights. These colorful displays occur near the Earth's magnetic poles and are a stunning natural phenomenon. Magnetosphere. The Earth's magnetic field creates a region around the planet called the magnetosphere. The magnetosphere acts as a protective bubble that traps and deflects most of the solar wind particles, keeping them from reaching the Earth's surface. It's important to note that the Earth's magnetic field is not static and undergoes changes over time. In fact, the magnetic field has experienced reversals in the past, where the magnetic north and south poles have swapped positions. These reversals occur over long periods, spanning thousands of years, and are still not fully understood by scientists. Earth's atmospheric layers. The atmosphere is a layer of gases that surrounds the Earth and is held in place by gravity. It plays a crucial role in supporting life on our planet by providing essential gases, regulating temperature, and protecting us from harmful radiation. The Earth's atmosphere is primarily composed of nitrogen, about 78%, and oxygen, about 21%. The remaining 1% consists of trace amounts of various gases such as carbon dioxide, argon, water vapor, and other gases. The atmosphere is divided into several layers based on temperature changes with increasing altitude. These layers are the troposphere, stratosphere, mesosphere, thermosphere, and exosphere. Here's a brief overview. Troposphere. This is the lowest layer and extends from the Earth's surface up to an altitude of about 718 kilometers, 411 miles, depending on the location. Weather phenomena, such as clouds, occur in this layer, and it contains the majority of the Earth's air mass. Stratosphere. Above the troposphere is the stratosphere, which extends from the tropopause, the boundary with the troposphere, to an altitude of about 50 kilometers, 31 miles. The stratosphere contains the ozone layer, which absorbs and protects against a significant portion of the sun's harmful ultraviolet, UV, radiation. Mesosphere. The mesosphere is above the stratosphere and extends up to around 85 kilometers, 53 miles. It is the layer where meteors burn up upon entering the Earth's atmosphere. Thermosphere. The thermosphere is a layer with high temperatures but very low density. It extends up to an altitude of about 600 kilometers, 370 miles, and is where the International Space Station orbits. The auroras also occur in this layer. Exosphere. The exosphere is the outermost layer of the atmosphere and gradually merges with the vacuum of space. It extends from the thermosphere up to thousands of kilometers into space. Functions. The atmosphere serves several important functions. Air and gas exchange. It provides the necessary gases, primarily oxygen, for respiration by plants, animals, and humans. It also enables the exchange of gases, such as oxygen and carbon dioxide, through processes like photosynthesis and respiration. Climate regulation. The atmosphere helps regulate the Earth's temperature through the greenhouse effect. Certain gases, such as carbon dioxide and water vapor, trap heat in the atmosphere, preventing it from escaping into space and maintaining a habitable climate. Protection from solar radiation. The ozone layer in the stratosphere shields the Earth's surface from harmful ultraviolet, UV, radiation by absorbing much of it. Weather systems. The interactions between the atmosphere, land, and oceans give rise to weather patterns and systems, including wind, clouds, precipitation, and storms. Navigation and communication. The atmosphere allows for the propagation of electromagnetic waves, which is essential for various communication systems, including radio, television, and satellite communication. Understanding the Earth's atmosphere is crucial for studying weather patterns, climate change, and atmospheric science in general. Tectonic plates refer to the large, rigid pieces of Earth's lithosphere, the outermost layer of the Earth, that move and interact with each other. The theory that describes these movements is known as plate tectonics. According to this theory, the Earth's lithosphere is divided into several plates that float on the semi-fluid asthenosphere beneath them. Here are some key points about tectonic plates. Plate boundaries. Tectonic plates interact along their boundaries, which can be classified into three main types: divergent boundaries, convergent boundaries, and transform boundaries. A. Divergent boundaries. These boundaries occur where two plates move away from each other. This movement leads to the upwelling of molten material from the underlying mantle, creating new crust. Divergent boundaries often result in the formation of mid-ocean ridges and rift zones on continents. B. Convergent boundaries. Convergent boundaries are formed when two plates collide. There are three subtypes of convergent boundaries. Oceanic convergence. When two oceanic plates collide, one of them usually subducts, dives beneath the other, due to its higher density. This process can result in the formation of deep-sea trenches and volcanic arcs. Oceanic continental convergence. When an oceanic plate converges with a continental plate, the denser oceanic plate subducts beneath the less dense continental plate. This subduction can cause the formation of coastal mountain ranges and volcanic activity. Continental convergence. When two continental plates collide, neither is subducted due to their similar densities. Instead, the collision results in intense deformation, folding, and thrusting, leading to the formation of large mountain ranges. C. Transform boundaries. Transform boundaries occur where two plates slide past each other horizontally. They are characterized by prominent fault lines, such as the San Andreas Fault in California. Transform boundaries neither create nor destroy crust but rather accommodate the horizontal movement between plates. Plate motions. Tectonic plates move due to the convective currents within the Earth's mantle. These currents are driven by heat generated from radioactive decay and residual heat from the Earth's formation. The plates can move at rates ranging from a few millimeters to several centimeters per year. Plate interactions and effects. The interactions between tectonic plates give rise to a wide range of geologic phenomena and features. These include earthquakes, volcanic eruptions, mountain building, the formation of ocean basins, and the shifting of continents over millions of years. Earthquakes. Plate boundaries are often associated with seismic activity, as the stress and strain accumulated by the movement of plates are released in the form of earthquakes. Volcanism. Volcanic activity is primarily concentrated at plate boundaries, particularly at convergent boundaries where subduction occurs. As one plate subducts beneath another, magma can rise to the surface, leading to volcanic eruptions. Mountain building. The collision of tectonic plates at convergent boundaries can result in the formation of large mountain ranges, such as the Himalayas and the Andes. Formation of ocean basins. Divergent boundaries contribute to the creation of new oceanic crust, leading to the formation of ocean basins and mid-ocean ridges. Continental drift. Plate tectonics provides an explanation for the movement of continents over geological time. The theory of continental drift states that continents were once part of a single supercontinent called Pangaea and have since drifted apart to their current positions. Studying tectonic plates and their interactions is essential for understanding Earth's geology, predicting the surface of the Earth refers to the outermost layer of the planet, encompassing the land masses, bodies of water, and various geological features. Here are some key aspects of the Earth's surface. Continents. The Earth's surface is composed of several large land masses known as continents. There are 7 continents: Africa, Antarctica, Asia, Europe, North America, Australia, and South America. These continents are made up of different types of rocks, soils, and geological formations. Oceans. The Earth's surface is predominantly covered by oceans, which are vast bodies of salt water. The major oceans are the Pacific Ocean, Atlantic Ocean, Indian Ocean, Southern Ocean, and Arctic Ocean. Oceans play a vital role in regulating the Earth's climate, storing and distributing heat, and supporting diverse marine ecosystems. Landforms. The Earth's surface features various types of landforms, including mountains, valleys, plains, plateaus, deserts, hills, and coastal areas. These landforms are the result of tectonic activity, erosion, weathering, and other geological processes that have shaped the Earth's surface over millions of years. Mountains. Mountains are elevated landforms that rise prominently above their surroundings. They are typically characterized by steep slopes and peaks. Mountains can be formed through tectonic processes such as volcanic activity, subduction, and collision of tectonic plates. Examples of well-known mountain ranges include the Himalayas, Andes, Rockies, Alps, and Mount Everest, the tallest mountain on Earth. Rivers and lakes. Rivers and lakes are prominent features on the Earth's surface. Rivers are flowing bodies of water that typically originate from highlands or mountains and flow towards lower elevations, eventually emptying into lakes, seas, or oceans. Lakes are large bodies of water surrounded by land. They can be formed through various processes, such as tectonic activity, glacial activity, or volcanic activity. Some famous rivers include the Amazon, Nile, and Mississippi, while notable lakes include the Great Lakes in North America, Lake Baikal in Russia, and Lake Victoria in Africa. Coastlines. Coastlines represent the boundary between land and sea. They can be characterized by various features, including beaches, cliffs, bays, and estuaries. Coastal regions are influenced by the interactions between land and sea, and they support unique ecosystems and human settlements. Islands. Islands are landmasses that are completely surrounded by water. They can be found in oceans, seas, lakes, or rivers. Islands can be formed through volcanic activity, erosion, or as a result of rising sea levels. Examples of notable islands include Hawaii, the Maldives, the British Isles, and the Caribbean islands. Geological features. The Earth's surface also encompasses diverse geological features, such as canyons, caves, fjords, dunes, deltas, and coral reefs. These features are shaped by geological processes, including erosion, deposition, and weathering. The surface of the Earth is dynamic and constantly changing due to geological forces, erosion, weather patterns, and human activities. It is a complex and diverse environment that supports a wide range of ecosystems and provides habitats for countless species, including humans. To get more informational videos like this, please subscribe our channel, share and press the bell icon. Thanks for watching.